So, welcome to the last day of SOC 2. Congratulations, you're here. You're not dead. The world didn't burn down. Even sequences in series are not too intimidating now. I want to talk about finding areas in polar coordinates today. That's our last topic. But before I do that, I know that there is some suffering involved with learning mathematics. I'm glad to see that you guys have a good sense of humor about it. So before we dig in, into this last topic, first some announcements. A little bit later today, I'll be releasing exam 3, which is the take home. I'll be posting that to Canvas. Remember that study guide 3 which is also homework 11 in WebAssign. This is due on Tuesday. So is exam 3. And then the final itself is going to be on Tuesday. Which is the 11th. And for you guys, it's from 10:30 to 12:30. The format for the final is going to be the same as the format for exams 1 and 2. So the final exam is going to be in Canvas. It's going to be proctored by HonorBlock. And I have very little room for flexibility with this time window. So Santa Fe has a strict policy about when final exams take place because other classes, because the final exam isn't during normal class time, we need to make sure that everybody's available to take the finals for the classes they're registered in. And in order to make that happen, they have a super strict schedule that I'm not allowed to deviate from. So I want everybody to put this shit in their phone right now. All right, set an alarm, do whatever you gotta do to make sure that you are up, awake, and ready to go at 10:30. I'll probably have the window open from like 10:15 to like 12:45, and then you can use whatever 2-hour block within that 2.5 hour window you want to. But it's very important that we don't mess up this timing. Because like I said, in order to change that, in order to give somebody the final exam at a different time, I have to get permission from my department chair. She has to clear it with professors in other departments. It's not a simple thing. The final exam is very similar to exams 1 and 2 in format. There's going to be some true false, some multiple choice, and some free response. It is comprehensive. It covers everything from the whole semester. And it's a little bit longer than exams 1 and 2. But not much longer. So I'll be grabbing a few of the most important problem types from each of the previous tests. Test 3 is not timed. Nope. I'll be posting the test today, and you can work it as much as you want until Tuesday. But you need to print it. So this is something that I am asking. I'll show you in just a minute. I'll show you what exam 3 is going to look like. But I'm asking that you please print exam 3. If you don't have access to a printer, and there's absolutely no way for you doing that, you can write out the solutions on your own blank paper. But if you do that, please be very organized. Like write the problem number, write the problem itself, and then write your solution. Make sure the free response problems are just like one solution per page. One of the reasons I'm insisting that people print exam 3 is because the organization structure there allows me to grade much faster, and I have to get this stuff turned around quick. Having the take-home to grade, new study guide to grade, and the final to grade all in just a few days is very, very hard. So I need you guys to work with me here. So please find a way to print exam 3 if you can. That would mean a lot to me. It will help everything go nice and smooth. I'm going to answer these questions in the order they came in. So the format of exam 3, I can show you. It's going to be here's my stuff from last summer, so it'll be different, but it'll be something like this. Is this Cal 2? Yeah. Right, so it's going to look like this. Different questions, of course, but it's going to look like this. So some true, false, some multiple choice, and then some free response. So you'll print and fill that out, scan and submit by Tuesday of next week. I do recommend studying the old exams to prepare for the final. First and foremost, make sure you do the homework, because the homework is where you practice and you build the skills that you need. But yes, once you have finished all the homework and you've written out your study guide 3 solutions nice and carefully and you're confident with all of that, then the next thing I would do is go back and study the old exams, because I am going to be using the old exams as inspiration when I write the final. So I'll be doing that. I'll be looking back at the old tests and kind of picking and choosing concepts that I want to move from them onto the final. Fernando, if you print exam 3, then you can use the provided space there. So it's precisely that. It's the format control that's so nice about printing it. So I leave plenty of space for you guys to answer questions in here. All right. Lots of blank space. So if you do print exam 3, you will not need to worry about the formatting. Just fill it out on the page. If you don't print it, then I do ask that you do the free response questions, 1 problem per page. The final exam is not going to have questions taken straight from exams 1, 2, or 3. Like I'm not going to just copy paste questions from one to the other. That would be a little bit silly, but I will be looking to exams 1, 2, and 3 for inspiration as I write the questions for the final. And so they will be the same concepts and same problem types that you encountered on exams 1, 2, and 3. So in other words, it is comprehensive. Okay. Yeah, so as always, the best way to prepare is to practice solving problems. I don't know, Shen, I actually haven't written it yet. So the final exams, I'll show you the final that I wrote for last summer, or I guess this is 2 summers ago now. So this was the final from a couple summers ago. And you can see some familiar looking things here. I think I had a total of, it's like 12 true, false, multiple choice, and then 18 questions altogether. Yours will probably have a little bit less because we're doing it online, and I know that this whole procedure is a little bit annoying and takes a little bit more time, but somewhere in the 15 to 20 range probably. Okay, any other questions before we get into the material? It won't be too bad. I will say this, if you're worried about grades, if you're panicking, does panic have a K? Panicking about grades. Come see me in office hours today. In some cases, I can do late withdrawal. In some cases, I can give an incomplete grade for the semester and then let you finish material up in the first few weeks of fall. But all of those things need to be sorted out by today at the latest. So I'll say that again. If you're panicking about grades, if you're worried that you're in a position where you can't possibly succeed in the course, where you're going to earn like a D or an F and it won't be okay moving forwards, come see me in office hours today and we can talk about the options. I can sometimes do a late withdrawal. It depends on whether you're dual enrolled and what kind of financial aid you get and a whole bunch of other things. So I can't make any promises, but in many circumstances, I am able to do something like that. But the last day I'm able to do that is the last day of class, which is today. So if you're in that panic state where you're like, oh, fuck, there's no way this could possibly go well, what do I do? Don't just like set it down and let it burn. Come talk to me and we can figure something out. Whether it's a late withdrawal or an incomplete or something else, we can talk about it and get it figured out. So yeah, I think with that said, let's cover the last little bit of material. Shen, I would recommend the homework, especially the problems that I've chosen to put on study guides, old exams. And then if you get through that, I would just go to the book and start solving problems from sections that you find challenging. So if your worst section was the section on the comparison tests, then I would go back to that section and work a bunch of problems. But first and foremost, I would say study the old exams, then study the study guide problems. Make sure you've done all the homework. And then and only then, if you still want more practice after that, I would just start going and picking challenging looking problems from the sections of the textbook that you found most hard. Okay, so areas and polar coordinates. This is section 10.4. The grading scheme for exam 3 and the final is the same as the grading scheme for all of my other exams. So there's partial credit on the free response problems, but not on the true, false, or multiple choice. And yeah, I'm happy to pop open any old homeworks that you guys want, but do submit an extension request. So I'm not gonna like open all of them by default, but if there's any old homework that you wanna go back and look at, you can of course always go back and review, but if you need to go back and complete things for credit, then submit an extension request in WebAssign and I will pop those open for you. So your book does talk about differential calculus in polar coordinates, but it's boring, it's not exciting. What is exciting though is the area problem, because of the symmetries that we see in some of these graphs. Area problems and in higher dimensions, flux problems are fascinating in these symmetric coordinate systems. So what we're going to talk about is specifically how to find areas. Which means we need to talk about a Riemann sum, because we're in a totally new coordinate system. We can't lean on anything that we have in the past. So if I have some curve here where r is a function of theta, which is how we usually graph those things, and I want to find the area from some angle theta 1, or call it theta 0 down here, call it alpha, why not? So this would be the polar point r of alpha comma alpha. And I want to find all the area enclosed in this wedge that's determined by my curve, my polar curve. So this would be r of beta comma beta. If I want to find all this area, the way I do that is by chopping up into a bunch of little pieces. And approximating each of those little wedges with a triangular thing. And this is where our polar Riemann sums will come from. And then we'll see how that Riemann sum passes to an integral, kind of like we did for the arc length when we talked about parametric curves. Okay. All right. So something like this. And then each of these regions I approximate as being sectors of a circle. So the basic idea is that each one of these guys, we chop the theta interval from alpha to this guy here, which is beta. The theta interval alpha beta into n equal sized subintervals of length beta minus alpha over n, and consider and approximate the areas in each wedge, in each, this is called delta theta, in each delta theta wedge as sectors of circles. So I imagine here that I have like, this is the one coming from, call it theta I minus 1, and this is the one coming from theta I. Then the area in here, which is this one, right? Yeah. The area in here, I can pretend is the area in the sector of a circle. So it's like I pretend like this is a constant function, just like we do when we use Riemann rectangles. So this point right here is coming from theta I. This point right here is coming from theta I minus 1. So the little angle inside is delta theta. So if you remember how to find the area of a sector of a circle, Ryan, I will try to get this recording up today, yeah. So remember the area of a sector of a circle shit, I can't draw. If you have some theta-sized wedge here, then this area has to be a linear function of theta, because when theta is 0, the area is 0. When theta is pi, the area is half the whole circle. And it has to be a quadratic function of the radius, because we know the area of the whole circle is pi r squared. It's 1/2 r squared times theta. And you can check if you plug in like theta equals 2 pi, then you get pi r squared, the whole area of the circle. So what we set up here is chop the theta interval alpha beta into n equal sized subintervals of length beta minus alpha over n. We call that length delta theta. And then we approximate the areas in each delta theta wedge. So like here's a wedge, here's a wedge, here's a wedge. We approximate each of those wedges, like the one I've shaded here is the one I'm going to use for actual calculations. We pretend like this wedge is the sector or a sector of a circle. Even though the actual curve might not be perfectly circular, it's a lot like in Riemann sums when you pretend that the graph is piecewise constant and you approximate using rectangles. Here, the analogous concept to a Riemann rectangle is this Riemann wedge. Right? And this should be coming into a point at the origin. I'm just a bad artist. So each of those little wedges, we can approximate their area as though they are sectors of circles. That's what we're going to do. So I say here we chop the theta interval alpha beta into n equal size subintervals of length beta minus alpha over n. Call that delta theta. And then approximate the areas in each delta theta wedge, like 1 wedge, 2 wedge, 3 wedges. Approximate each of those wedge areas as sectors of circles. So each delta theta wedge has area approximately equal to 1/2 r squared of that theta, I'll call it theta I, times delta theta. Right, so this guy is r of theta I, comma theta I. That's the polar coordinate there. This guy is r of theta I minus 1, comma theta I minus 1. So I pretend like this wedge is actually a part of a perfect circle, even though it's not, right? Because my curve does all sorts of weird things. It's not a circle. I just pretend like each wedge, because they're small enough, I can approximate them as circular wedges. If they were a perfect circle, then this would be exact. But as it is, it's just an approximation. And then from here, we build a Riemann sum. So the total area enclosed by the polar curve r equals r of theta from theta equals alpha to theta equals beta is approximately A equals, I'm adding up all of these little wedge areas. So that's the sum from I equals how many wedge areas do I have? Well, I split this into n equal length subintervals. So that's from I equals 1 to n. And then each one of the little areas is like this. So my sum is 1/2 r squared of theta I, or you can write it as r of theta I all squared times delta theta. And I suppose I should use an approximately equal to here, right? Because this is an approximation. But then we recognize this as a Riemann sum. For the exact area and if we translate that Riemann sum into an integral, the integral is the integral from alpha to beta, 1/2. You don't integrate the function r, you integrate r squared. So r of theta all squared d theta. And that's it. So why do we do an arc tree calculation? I don't fully understand the question. Nick, could I ask you to be a little bit more detailed? What do you mean, why wouldn't we do the area of an arc? That is what we're doing, right? So we're finding we're finding the area of this like circular arc wedge. And each one of those has area 1/2 times this radius time, squared times delta theta. So delta theta here becomes d theta. What we do is we send n to infinity, right? And remember in your Riemann sums, when you send n to infinity, what you end up with is an integral. The delta theta turns into a d theta. R squared of theta I, or r of theta I all squared, just becomes r of theta squared, and the 1/2 comes along for a ride. I think I understand what you're asking, Nick. So why can't I just use geometry to calculate the area bounded by this curve? Because the radius isn't constant, right? That's the idea, is that in these polar curves, the radius changes. It's a function of theta. So we'll look at a few more explicit calculations and graphs today, and I think it'll help you see. But if the radius was constant, then yeah, I could just use geometry. But here the radius is a function of theta, so it's curving, it's changing all the time. So what I have to do is chop it up into a bunch of little pieces, and then each one I can pretend is like a part of a circle, because the delta theta is small enough that the error there is very little. So it's a lot like when you look at regular Riemann sums for the integral of f of x. You know, your rectangles overestimate or underestimate in some places, but as long as they're narrow enough, you'll get very, very close. And then in the limit, it's exact. So there are probably some good GIFs of this on the interwebs. You want polar coordinates. And none of this shit looks any good. Let me pull Riemann sum off there. Let's see. Yeah, we're kind of getting there, but none of these have the picture with the wedges. Well, your textbook probably has an okay one. Let's take a look at that. This is 10.4 areas and polar coordinates. Yeah, this is the picture, right? So here in blue is your function r of theta or f of theta, and we chop into a bunch of little wedges. And each one of those wedges we can pretend is a circle with a constant radius. Now, of course, that's not true. It's only an approximation. But as we use more and more wedges, we get a better and better approximation. So that's the game. We're after an area like this. We approximate it by a bunch of little wedges, and we get this formula out. So then the game is going to be to look at some polar curves like these guys and try to find some areas like this. So let's do that. So good news, here's the last formula you learn in Calc 2. Yay! This is the area enclosed by the polar curve r of theta between the angles alpha and beta. Yeah, in fact, it's impossible to do with raw geometry. You need calculus because the curve is non-constant in radius. Okay. So I think last time we finished by graphing r equals 2 cos theta. I'd like to graph something a little bit more exciting here. So let's graph r equals, how about sine of 2 theta? So let's find the area enclosed by one loop. First, of course, we're going to have to draw the graph. And in order to draw that graph, remember our procedure. First, we graph in rectangular coordinates. That's normal, like Cartesian stuff. And then we transfer the graph bit by bit into polar coordinates. So first we graph in rectangular coordinates. Always at least from 0 to 2 pi, because I want to know in my polar setting how we go around. Simon, I don't think I want to graph that. That looks a little frightening. So let's keep it a little more tame. Of course, you can use Desmos to get a look at these graphs, but getting to a place where you can visualize them reasonably quickly is a meaningful skill. Okay, so let me call this 2 pi. I know that sine 2 theta is periodic, and the period is actually pi. So we're going to go through 2 full cycles of this sine wave between 0 and 2 pi. The amplitude is 1. So we'll go from a min of -1 up to a max of 1, and we start at 0. And I know that I'm going to go through a full cycle from 0 to pi. So here at pi over 4, because this is pi over 2. And here at 3 pi over 4, we'll be at our min. So my graph in rectangular coordinates looks something like this from 0 to pi. And then he does that same shit again from pi to 2 pi. So I'll be going through here, I'll be up at my max here, I'll be down at my min here. Okay, and we always want to label kind of all of these important points, any intercepts, mins, or maxes on my rectangular graph. So this is sine of 2 theta. This vertical axis is my r axis, this horizontal axis is my theta axis. This is the normal graph of sine 2 theta. If this is pi and this is pi over 2, then this has to be pi over 4. So this is 3 pi over 4. This is pi, this is 5 pi over 4. 6 pi over 4, 7 pi over 4. All right. And now what I do is I take this graph and bit by bit transfer it into polar coordinates. And I like to think about that arm kind of spinning around and the dude moving in and out on the arm, drawing the graph. I know we start with r equal to 0 down here. So when theta is 0, r is 0. Let me draw in some little helper lines at the multiples of pi over 4. So here's the line theta equals pi over 4, or the ray theta equals pi over 4. Over here I have the ray theta equals 3 pi over 4. 5 pi over 4 down here. And 7 pi over 4 over here. You may want to print up some of that polar graphing paper that I showed you guys last time. As you get comfy graphing these, that can be very helpful. So what happens in this first little region here, right, over here? Well, as theta increases from 0 to pi over 4, r goes from 0 out to 1. So let me first plot the polar point 1 comma pi over 4. I know that's on my graph because when theta is pi over 4, r is 1. And what happened in between 0 and pi over 4? Well, as my little arm starts to spin around, my little guy runs from the origin all the way out to radius 1. So if you follow the path that my finger took along the paper there, it would be some sort of curve, some sort of bloopy little curve coming tangent out here at the x-axis, at the horizontal or polar axis, and up like this. And now as theta continues from pi over 4 towards pi over 2, as my arm rotates from pi over 4 to pi over 2, all right, so we got to think about this real carefully. So the thing we're looking at here, the height here is the radius here, and the length here is the rotation here. So when theta is 0, I haven't started to rotate at all, and my radius is 0. If I increase theta a little bit, looking along this graph, like right here, theta has increased a little bit, so my arm has rotated just a little bit, and my radius has increased a little bit. A little more theta, a little more r, a little more theta, a little more r, a little more theta, a little more r, until I get to this point right here, where r reaches its maximum of 1. And that's when theta is pi over 4. So as I rotate past pi over 4, what's going to happen? Well, my radius starts decreasing, right? If I think about being like right here, a little bit past pi over 4, my radius, rather than being all the way out at 1, should have come in a little bit. And if I look a little further, my radius will be a little smaller. A little further, my radius will be a little smaller. A little further, my radius will be a little smaller. Until we get to this guy right here at pi over 2. So by the time this arm is straight up and down, my radius is all the way back into 0. So I'll be drawing something like this, and I'll come in tangent to the vertical axis there. Because this isn't sine x, this is sine of 2x. Remember, we're graphing, or sine of 2 theta, I should say, not sine of 2x, sine of 2 theta. So remember, multiplying on the inside of a function by any number compresses it horizontally. Or if you like, you can calculate the period. The period is always 2 pi divided by whatever that multiple is inside here. So that's pi. So this is a sine wave with amplitude 1 and period pi. I got you. So yeah, it's because the graph has been horizontally compressed. Here's one full period for this function. The period is pi. So from 0 to 2 pi, we go through 2 full cycles. R always goes in the first coordinate, and theta always goes in the second coordinate. I wouldn't say this is x and this is y, because x usually means horizontal and y means vertical. Here, this means radius and rotation. But yeah, first coordinate is r, second coordinate is theta. Yep. Yeah, so our polar coordinates are always r comma theta. That kind of bothers me too, because usually we think of the first coordinate as being the independent variable and the second coordinate as the dependent variable. And here, theta is really the independent variable. We're asking, what does r do as theta changes? But that's the system. I don't know. It's a convention. I think because usually when people first learn how to plot polar coordinates, they tell you pick a circle, pick a radius, and then rotate. So but you can just as easily rotate and then walk out. So it's just a convention. Why does x come first in rectangular coordinates? Because Descartes chose to write it that way. So this first guy here, this first hill, corresponds to this first loop. This second hill, however, r is negative. Now that's from theta equals pi over 2 to theta equals pi. So that would usually mean we're drawing over here. Right? It would usually mean, I'm left-handed, so this is a little hard for me. Usually means we're drawing over here from theta equals pi over 2, which is here, to theta equals pi, which is here. But unfortunately, because r is negative, we're going to have to reflect all that shit through the origin. Because remember, when the radius in polar coordinates is negative, you have to reflect through the origin. So we know we've got the point pi over 2, where theta is pi over 2, r is 0. So we're back here at the origin when the arm is straight up and down. And as I rotate past that just a little bit, r is going to be poking out, but it's negative. So rather than poking out in this direction, it's going to be poking out in this direction. So as theta rotates just a little bit past pi over 2, r starts poking out like this, until we get to the point 3 pi over 4, where theta is 3 pi over 4 and r is negative 1. So 3 pi over 4 and positive 1, or 1 comma 3 pi over 4, that would be over here. Negative 1 comma 3 pi over 4, therefore, is over here reflected through the origin. This business is very important because if I ask you for a particular area, you need to know what theta range to integrate. And at a glance, this is going to look like it should be from 3 pi over 2 to 2 pi, but it's not. It's coming from the pi over 2 to pi range because r is negative there. So we reflect everything through the origin. And what we get, you can see from the symmetry of the original rectangular graph, we'll get a symmetric looking piece over here like this. So remember, when r is negative, you reflect the polar coordinate through the origin. So over here would be the point 1 comma 3 pi over 4. I don't want to write it here because I don't want to clutter this with stuff. Here's the polar point 1 comma 3 pi over 4. So the polar point negative 1 comma 3 pi over 4 is down here reflected through the origin. And when theta is 3 pi over 4, r is negative 1. So the point I'm looking for in my polar graph that corresponds with this point in the rectangular graph is over here. He's reflected through the origin from 1 comma 3 pi over 4. So that gets me out here. So this min corresponds to this point. And the way I do this when I teach this in trig is I would say this portion of the arc up here, this dark shaded part, this bolded part, corresponds to this bolded part of the curve here. And if you just look at the finished picture, it will not be obvious that this piece came from theta values between pi over 2 and 3 pi over 4, because usually those would be up here. But because r is negative there, it's all reflected through the origin. It's true, Simon, that the area of these two loops we've drawn so far are equal to one another. And then you can also kind of see what's going to happen using symmetry arguments from here, right? So now we've come back into 0. We're back at the origin again when theta is equal to pi. As theta rotates past pi towards 5 pi over 4, that's going to be drawing over here. And since r is positive, I don't have to worry about any reflection through the origin until I get to 5 pi over 4, which is this ray, and a max of r equals 1. So I get out to the polar point 1 comma 5 pi over 4. And that arc looks like all the other arcs that we've seen here so far because of the symmetry in the graph, symmetry in the rectangular graph. So I get something looking like this. And then as theta rotates past 5 pi over 4, we come back into the origin and we get there. And then finally, as we rotate through this last theta interval from whatever this would be, 3 pi over 2 to 2 pi, we're going to poke back out. And normally between 3 pi over 2 and 2 pi, we'd be drawing over here. But because r is negative again, we'll be drawing in the reflected space over here. And we'll do the same thing. We're going to come out to a max radius of 1 and then run back into the origin. So I'm going to do at least one more example where I draw a graph like this for you guys today, but this is called a petal graph or a flower graph. And sine nx or cos nx, they all look like this in polar coordinates. The orientation, like how the petals are arranged, and the number of petals can be deduced reasonably easily from the number inside the sine function or cosine function. If this number is even, then you'll have, so sine nx is a petal graph. So sine r of theta equals sine n theta is a flower graph. And if n is even, there will be 2n petals. If n is odd, there will be n petals. And there's a similar rule for cos n theta graphs also. So I'll look at some examples real quick, and then we're going to do an area calculation. Your book does talk about this. I think they even have a table where you can like memorize some of the basic polar graphs. But the skills I want you to practice are precisely what I've shown here. Drawing the rectangular graph and then transferring it over into polar coordinates. Still, it's useful to know this shit because you can check your work. So first, let me show you where this is in the textbook. It's probably at the end of 10.3. You see them doing some graphing here. They call it a rose. Yeah, here I see a 4-leafed rose. This is a cosine rose, and I can tell that because the first petal is aligned along the horizontal axis. Yeah, this is cos 2 theta. And then somewhere down here, they have a summary of the basic ones. Oh, maybe not. Yeah, maybe that's just in the trig book. Oh no, here it is, families of polar curves, yeah. So n theta, sine n theta, and cosine theta, what happens if you replace it by the absolute value? All that good stuff, but maybe they don't have that here. No, they don't. All right, I can post a link, but let's go play in Desmos for a minute. My Calc 1 class is doing some curve sketching. We're doing curve sketching, but we're doing it in polar coordinates. So we just graphed r equals sine 2 theta. What's going to happen if I graph sine 3 theta? How many petals will sine 3 theta have? Yeah, here it is. So you see here in green, r equals sine 3 theta. And because n is odd, you have exactly n petals. Sine 4 theta is going to have 8. Sine 5 theta is going to have 5. And you see they're always oriented like this. Because you always start out at the origin. So you always begin by poking out from the origin. If I swap the sines to cosines, they're rotated so that you begin out here. When theta is 0, r is at its max, because cosine starts out at its max value. And of course, if you start multiplying by numbers in front of these, you scale them, because you're just scaling up the radius. Cos 2 theta will have 4 petals, but it'll be arranged so that your petal is along this positive horizontal axis. And because I put a 5 in front of it, I've scaled everything up by a factor of 5. Okay. But we can always cook them up as we need, just by being patient, drawing the rectangular graph, and transferring it over point by point. Let's find the area enclosed by one of these petals. I want to make a note here. I'll start it down here. So find let's say I want to find the area enclosed by r equals sine 2 theta in Q4. So we could say that, yeah, all these petals have the same area. So I could find the area of this first petal, and that'll be the same as the area of this guy down here. But I want to emphasize that it's not super obvious that the area we're looking for down here comes from the theta values it does. So let me shade this. This is the area I'm going to find. This area is associated with the theta interval. I don't know why my pen isn't working. The theta interval pi over 2 to pi, even though it's down here in quadrant 4. Because remember, when we came past pi over 2, r was negative. And so this was actually drawn here as theta ran from pi over 2 to pi. Remember, this dark shaded part of the graph here gave us this dark shaded part of the graph here. I want to make another comment, and that's that this area is not the same as this area. It's not just that I've drawn them in different scales. This area is not the same as this area. So you cannot calculate this area using the earlier techniques and deduce this area is the same, because they are not. Changing the coordinate system actually changes the geometry. So that petal came from the interval pi over 2 to pi. So I'm going to integrate from pi over 2 to pi. And then remember our formula. We integrate 1/2, not r, but r squared. So this is, I'll write it as r squared of theta d theta. And that's the integral from pi over 2 to pi of 1/2. What is r? Well, r is sine 2 theta. So this is sine 2 theta all squared d theta. So are we comfy with why this guy comes from the pi over 2 to pi interval? That tends to be the hardest part. Because if I just gave you this picture, you would say, oh, well, this is from 3 pi over 2 to 2 pi, because it's quadrant 4. But we have to remember that this petal came from a part of the original graph where r was negative. So it's really like a reflected version of this petal. It's really coming from what would normally be drawn over here, reflected through the origin. So that's pi over 2 to pi. Even if you fuck that up here, the calculation would come out okay, because these all have equal areas, as Simon noted. But not every polar graph has exactly that symmetry. So this is an important thing to be able to see. From here, the calculation is fairly trivial. We've done lots of integrals like this. This is 1/2 integral pi over 2 to pi sine squared of 2 theta d theta, and we integrate even powers of sine, always by using half angle identities. So there's going to be another copy of 1/2 coming out, which will make that 1/2 a 1/4. And then I'll have pi over 2 to pi, 1 minus cosine of the double of this, which is 4 theta d theta. So I use my double half angle thing because it's an integral of an even power of sine. And now everything is nice and straightforward. I can find an antiderivative here simply enough. It's one of those micro u subs that we're now fast enough at. We can do them in our head. 1, of course, integrates to theta minus cos 4 theta integrates to sine 4 theta over 4. And I need to evaluate this between bounds, pi over 2 and pi. If I plug pi in, the sine of 4 pi is 0. If I plug pi over 2 in, the sine of 4 times pi over 2 is the sine of 2 pi is also 0. So the only contribution comes from the theta piece here. And that's going to be pi minus pi over 2. Pi minus pi over 2 is pi over 2. 1/4 times pi over 2 is pi over 8. So this is finding areas in polar coordinates. It's not bad. The hardest part is drawing the graph and figuring out your bounds, figuring out the theta values that correspond to the part of the graph you want. I want to make very good use of our time here today because this is our last day. I want to graph a different kind of polar curve, something called a limison. Any questions about this integral before I move away from it? Any one of these steps we'd like to look at a little bit more closely? I know it's been a while since we did these back in 7.2. That's the hard part, right? Is figuring out the bounds. Because this loop was drawn when we got to this part of the graph, right? My arm rotated from 0 to pi over 4, I drew this thing. From pi over 4 to pi over 2, I drew this thing. But then as we rotated past pi over 2, r was negative. So we had to be drawing down here. So remember, this shaded part of the graph in the rectangular coordinate picture, this part, is when we drew this guy down here. Oh, why not 2 pi? Yeah, yep, yeah, good, okay. So Caesar and Lucas are asking two good questions. I don't think they're directly related to each other, but they're both not super obvious. So the part of the graph that we transferred to get this piece here was from pi over 2 to pi, right? This stuff actually came from pi over 2 to pi, even though it doesn't look like it in the final picture. So that's the theta interval over which I need to integrate in order to say for sure I'm getting this area. So this will take some practice, and that's why I want to get to another example. I want to get more practice with the graphing. So I'd like to look at what's called a limison next. I think I can get one of those by doing about, need it to be negative sometimes. So let's do, how about 3 cos theta plus 1? Yeah, 1 plus, we can even do 1 plus 2 cos theta. Is that going to be too much? Bump this up. No, I think this will be good. Yeah, so let's sketch the graph. And once we have the graph, I'll set up an area problem for us. Limison, so I suspect this is going to be what's called a lim, and then it's got this funny like Turkish accent mark, O-M. Limison. There might be an S here. Spelling is not my strongest point. Is there an S? No S. It's as I spelled it. Yeah, okay, good. There's also something called a lemniscate. I think you definitely see this in Turkish. I don't remember this accent mark in French. What's it called? I used to know a little bit of French. A cedille? Cedille? Cool. All right, thank you for teaching me something today. Limison does sound like a French word, doesn't it? Cedia. Cool. All right, so if I want to graph 1 plus 2 cos theta, I know that's a cosine wave of amplitude 2 that's been bumped up by 1. So I'll call this 1, and I'll draw in my like equilibrium line to help me out. We're going to go up as high as 3. I need to get into the territory there. And we're going to go down as far as -1, right? Because my amplitude here is 2. So we go down 1, 2, and we get down to -1. And then the cosine wave from 0 to 2 pi, we should be back up here by 2 pi at let's see, at pi over 2, we're 0. At pi, we should be all the way down at -1, our min. And then halfway in between, we should cross this equilibrium. We should be crossing like that. Up here, we look like this. Over here, we look like this. So my cosine wave here looks like this. Ah, that's cool. Oh, you guys know a lot about the vernacular here. That's new to me. So French for cochlea, like the ear. And Fernando says that that character is also used in Old Spanish. Nifty. Okay, so I want to label any of the important points here, mins, maxes, and intercepts. This is, of course, theta is 2 pi, and r here is 3. These guys, I'm going to have to do a little bit of work to find. Here, of course, theta is pi, so this is theta equals pi, and r is -1. And over here, theta is 0, and r is 3. But in order to find these horizontal intercepts, I'm going to need to solve the equation r of theta equals 0, which means 1 plus 2 cos theta equals 0, which means cos theta is -1/2. And there's two solutions to that. Catalan, that's cool. So cos theta is -1/2, 2 places between 0 and 2 pi. That is going to be pi over 3. Pi over 3. Sorry, 2 pi over 3. 2 pi over 3, -1/2. 1 pi over 3, 2 pi over 3. And then also 3 pi over 3, 4 pi over 3. So here, theta is 4 pi over 3, and r is 0. And here, theta is 2 pi over 3, and r is 0. So I've got my nice rectangular graph with all the important stuff labeled. And now I'm ready to transfer it into the polar coordinate system. So this is not a limison, right? This is just a cosine wave. But the result, when we transfer it over here into the polar system, is what's called a limison. When theta is 0, okay. We can all, let's return to the mathematics. When theta is 0, r is all the way out here at 3. So this is where we start for this guy. And now as my theta arm starts to rotate around, r is decreasing. So we'll be coming in. And by the time we get over here to 2 pi over 3, we'll be back at 0. So some other points that might be worth looking at, maybe this guy. So when is this apparatus equal to 1? Well, that's at pi over 2, where the cosine is 0. So up here, we'll have the point pi over 2, where theta is pi over 2 and r is 1. And then by the time we get to the 2 pi over 3 ray, which is like this, we will have come back into 0. So something like this is going on here. As theta runs from 0 to 2 pi over 3. The horizontal line here, y equals 1, is what we call the equilibrium. It's what normally would be the x-intercepts or the horizontal intercepts, except my cosine wave has been bumped up by 1. So I would be careful with words. I wouldn't say it's the origin. The origin is definitely always the point 0, 0. But analogous to the horizontal axis if the wave had not been shifted up. Here's the fun part, where r is negative. Between 2 pi over 3, which is here, and 4 pi over 3, which is symmetric down here. So this is the theta equals 2 pi over 3 ray, and this is the theta equals 4 pi over 3 ray. As we poke just a little bit into this territory where r is negative, normally between 2 pi over 3 and pi, we would be drawing over here because this is 2 pi over 3 and this is pi. If r were positive, we would be drawing over here during that. But we're not because r is negative. So instead, we'll be drawing in the symmetric region, which is down here. And what exactly happens? Well, r comes out from being 0. So we're going to be poking out from the origin. But rather than poking out over here in the positive space, we'll be poking out over here in the negative space. And we get to a kind of largest r value, or largest absolute value of r there, at pi and -1. So when theta is pi, pi comma +1 would be right here. This is the polar point 1 comma pi. So the polar point -1 comma pi is right here. So what we're going to be doing here is a little loop-de-loop like this. This is the part of the graph that corresponds to the dark shaded part in the rectangular graph above. And then as we rotate past pi towards 4 pi over 3, we do this. That corresponds with this part of the rectangular graph, because r is coming back towards 0, so we're walking back in towards the origin. We're rotating between pi and 4 pi over 3. Normally that would mean drawing over here, but because we're reflecting everything through the origin, that means we're drawing over here. And then once we come past 4 pi over 3, r is positive again, and everything starts to make sense. This piece of the graph is symmetric to this piece of the graph. So in the polar picture, we'll get something that is symmetric to what we had before. This guy right here is 3 pi over 2. So we'll have 3 pi over 2 comma 1 on my polar graph. Sorry, 1 comma 3 pi over 2. R equals 1. Theta is 3 pi over 2. This guy was -1 comma pi. And then we'll connect back over here to this piece in a symmetric fashion with the part above. So this is your limmason. And if I wanted to find some portion of area here, I'm going to have to be quite sneaky. If I wanted to find this area, it wouldn't be too bad because that corresponds to a part where r is positive, right? Specifically here. If I wanted to find the area, say, like this, where's something that involves r being negative? If I wanted to find the area of this inner loop, I need to know what are the theta values associated with that inner loop. And this inner loop here, even though it's in quadrants 4 and 1, which we normally associate with theta values like 0 to pi over 2 or 3 pi over 2 to 2 pi, came from this part where r was negative. So really, it's coming from what would normally be over here, the theta values between 2 pi over 3 and 4 pi over 3. So the shaded area here is the integral from 2 pi over 3 to 4 pi over 3, 1/2 1 plus 2 cos theta all squared d theta. Okay. So again, this integral isn't terribly hard. We can go ahead and calculate it, but the tricky thing is finding the bounds. You'll see this in Calc 3 too. When you talk about coordinate changes, like U substitution basically, in higher dimensions, by far the hardest part is figuring out how the bounds change. That's why I emphasize that so much when we started off in this course. So let's go ahead and calculate that integral. First, any questions about how we get this polar graph from this rectangular graph? So basically we're making a table, right? I mean, we can plot a bunch of points, one point at a time, by grabbing these really important points from my graph in rectangular coordinates and plotting them in polar coordinates. So the bold points here at 0, pi over 2, 2 pi over 3, pi, 4 pi over 3, this was 3 pi over 2, and r is 1. Those would give me this point, this point, this point, this point, this point again, this point, and then this point. But it's not immediately obvious just from those points to see how you connect it. How do we find the balance? You mean the bounds? What do we mean by balance? Bounds, yeah, okay. So I want to find the area of this loop, which means I need to identify what theta values correspond to this part of the curve. If you remember, this part of the curve right here, this dark shaded part, came from this dark shaded part. So the whole point here is when you go to set up an area problem, you have to have drawn the graph by hand in order to be able to realize, that's okay, yeah, I don't mean to give you a hard time at all. So in order to find these bounds, we have to remember, when did I draw this part of the graph? What theta values was I thinking about when I drew this little loop? Right here at 2 pi over 3, right here, is when r first contracted back to 0. So I know that this loop began at this theta value, which is 2 pi over 3. This is why we always calculate the important points on the rectangular graph before trying to draw the polar graph. So I know that this loop began right here, at theta equals 2 pi over 3, because that's the first time r got to 0. And this loop starts here at the origin where r is 0. This part of that loop came from this part of the graph, because this point, r is -1 and theta is pi, r is -1 and theta is pi. I drew that after coming through here. So this part of the loop came from 2 pi over 3 to pi. And then this part of the loop starts at pi. And when did we get back out? When did r come back to being positive? Well, right here at this horizontal intercept on the rectangular graph, which was 4 pi over 3. So I know that this loop inside here came from 2 pi over 3 to 4 pi over 3. So it's certainly not easy. It's definitely the hardest part of all this 10.4 stuff is identifying the bounds for the integrals. And the trick is to draw the graph carefully by hand. If you use graphing software, it's just going to give you this picture and you won't know which parts came from which theta values. But if you go through this process where you draw the rectangular graph and then imagine rotating around and sketching the curve, then you'll be able to remember which pieces of this graph came from which theta values. And this thing I did where I like shade a part of the graph here and shade a part of the graph here, or bold it, that can also be really helpful. Anytime I recognize that my polar graph is getting complicated, I like to come back to the rectangular graph and say, okay, I'm going to shade or bold this part and shade or bold the corresponding part on the polar graph to help me remember which horizontal values here correspond to which angles here. So let's go ahead and crunch this integral. It is equal to 1/2 integral 2 pi over 3 to 4 pi over 3. I FOIL that out and I get 1 plus 4 cos theta plus 4 cos squared theta d theta. And then I'll split that up. And this last piece is going to require a little bit of attention. Maybe I won't split it up yet. I'll just go ahead and apply the trig identity. So this is 1 plus 4 cos theta plus, here I'm going to use the half angle or double angle thing again. Cos squared theta is 1/2 times parentheses 1 plus cos 2 theta. So that 4 will become a 2, and I'll have 1 plus cos 2 theta here, like that. So I will actually have some like terms when I distribute this 2 over these parentheses. I'll have 2 plus 2 cos 2 theta, and the 2 from the 2 and the 1 will come together with this to make a 3. So I'll get 1/2 integral 2 pi over 3 to 4 pi over 3, 3 plus 4 cos theta plus 2 cos 2 theta d theta, like that. And now we're to a place where antiderivatives are easy to spot. So this is 1/2. 3 becomes 3 theta plus 4 cos theta becomes 4 sine theta plus 2 cos 2 theta becomes 2 sine 2 theta over 2, which is just sine 2 theta. And this is from 2 pi over 3 to 4 pi over 3. Right, so this piece would normally, without the 2 there, would integrate to sine 2 theta over 2. But then there's this 2 that cancels with the 2 that would be downstairs, so we get that. Here things are less obvious because we need to evaluate these functions at multiples of pi over 3. So I'll go ahead and write everything out. At 4 pi over 3, you'll have 3 theta is 4 pi plus 4 sine 4 pi over 3 plus sine of 8 pi over 3. That's my upper bound, and then I subtract what I get at my lower bound. 3 times 2 pi over 3 is just 2 pi. Plus 4 times the sine of 2 pi over 3 plus the sine of 4 pi over 3. And we can take a look and hope for some cancellation. I can definitely combine some terms. I've got 4 sine of 4 pi over 3 minus 1 sine of 4 pi over 3. I've got 4 pi minus 2 pi. So this guy will play together with this guy to give me 2 pi. This guy will play together with this guy. 4 copies of that thing minus 1 copy of that thing is 3 copies of that thing. So 3 sine of 4 pi over 3. And then the other 2 I just have to deal with. Sine of 8 pi over 3 minus 4 sines of 2 pi over 3. And then we think about our unit circle. The sine of, oops, sorry, here we are. So I'll come back to that, Lucas. It is definitely the hard part. And the trick is to make sure you're comfy as we drew the graph here. So we entered the origin here for the first time when theta is 2 pi over 3. And then we exited this loop when theta is 4 pi over 3. So that's why I drew these 2 rays in here. We can come back and talk about it a little bit more, but let's finish the calculation we're working on at the moment. So what did we say? We need the sine of 4 pi over 3. Let's see, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. The sign down there is negative root 3 over 2. The sine of 8 pi over 3, or let's see, 8 pi over 3 is the same as 6 pi over 3 plus 2 pi over 3. 6 pi over 3 is 2 pi. So this is the same as the sine of 2 pi over 3. That's positive root 3 over 2. And then minus 4 copies of the sine of 2 pi over 3, which is again root 3 over 2. So we have a lot of root 3 over 2 stuff. And what do we have all together? Oh, it looks like they're going to go away entirely. Yeah. Root 3 over 2 minus 4 copies of root 3 over 2. That's negative 3 copies of root 3 over 2. I don't know, they're going to come together. Yeah, they're not going to. So what do we get all together here? Let's just write it down. 1/2 2 pi. And then I've got minus 3 plus 1 is minus 2. Minus 4. So what do we'll have here? Negative 1, negative 7 plus 1, negative 6 of those. Am I doing that right? Minus 3 plus 1 is minus 2, minus 4 is minus 6 copies of root 3 over 2. So what is that? That's pi minus 3 times root 3 over 2. All right. Sorry, so here are all the calculations for this guy. I think everything fits there now, right? So let's talk a little bit more about bounds, finding bounds. We've got just a few minutes before I need to switch to the office hour. There's one last type of curve like this. If I take a sine or cosine wave and I bump it up so that it just barely touches the x-axis, like 1 plus sine x, or I guess 1 plus sine theta, call this 2 pi, and that makes this pi over 2, and 3 pi over 2, call this 2, 1, and of course 0 down here, then up to max there, down here. Is that right? Why am I feeling stupid? So I should be 0. Oh, okay, yeah, here, there we go. And then here, and then here. All right, I knew I was doing something wrong. So I'll show you what it is on graphing in just a second, and then we'll talk about transferring into polar coordinates. This is r equals 1 plus sine theta. Here, because we don't actually dip below the horizontal axis, I did a bad job drawing, but we don't actually dip below the horizontal axis, we just touch it there. We don't have any inner loop in the polar graph, but we do come in and just barely kiss the origin for a second. So if I start here, when theta is 0, r is 1, I'll call this 1. And then as theta increases from 0 to pi over 2, as I rotate like this, r gets larger and goes all the way out to 2. So here would be the polar point 1 comma 0, the polar point 2 comma pi over 2, and these are connected by a bit that looks like this. So this is coming from the theta range 0 to pi over 2. And then as I rotate past pi over 2 towards pi, I come back to 1. So here's the polar point 1 comma pi. And my curve there would look like this. So coming past pi now, so I rotate here. When r is 0, theta is 1. Sorry, when theta is 0, r is 1. And then as I rotate theta up past 0 towards pi over 2, r is growing. It is going to look like a cartoon butt, yeah. So as we rotate from theta equals 0 to theta equals pi over 2, r grows from 1 to 2. So my little dude is starting out right here. And as I rotate, he's slowly walking out until he gets up here to 2. And then as my arm rotates past pi over 2, where I have this max, now my little guy is going to start walking back in. He's going to walk in until he gets to 1. Then as I rotate past pi towards 3 pi over 2, he's going to keep walking in. So as I rotate past here towards here, my little guy is going to walk all the way into the origin. So this is the polar point 0, comma 3 pi over 2, coming from this point on the rectangular graph. And then as I rotate past 3 pi over 2, he's going to walk back out and join up over there. So this part came from pi over 2 to pi. This part came from pi to 3 pi over 2. And because r is never negative here, we never had to do any reflecting through the origin. But if I moved this graph down just a little bit so that there was a blip here beneath the origin, if I had something like this, then that would correspond to something like this. And the trick to remembering what theta values are associated with what part of the curve is to go through this procedure where you draw the rectangular graph and then imagine rotating around and running in and out along that arm. So as I rotate, I walk out, 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 and now I'm at that max. And then I walk in, and now I'm at this point, and then I walk in more. So this whole decreasing thing here corresponds to r becoming smaller everywhere through here. If r became negative, it didn't here, but if it did, like this dotted bit, then you would get something like this dotted little reflected loop in here, which would correspond to whatever values mark the parts where r is negative. So area is always positive. And because of the way, one way to think of it is that even if r is negative, our formula for the integral here involves the square of r. So we don't need to worry about signs as much. This formula, in other words, the area formula in polar coordinates is not signed area, right? Like when you look at an integral of a regular xy function, area beneath the horizontal axis is always measured as negative. Area above the horizontal axis is always measured as positive. There's no such issues here. In polar coordinates, the area will always be measured as positive. The integral does not measure signed area, it just measures enclosed area. So for example, if I had a limison, that thing we just drew here, by the way, sorry, it's called a cardioid. Because it kind of looks like a heart, right? It's like an upside down heart. if we did have a loop, if I had a limison, so let's assume something similar looking. But then we come in here and we get a loop like this. If I wanted to find, say, this area, not including the area inside the loop, just the area outside the loop, if this piece comes from theta equals alpha, and this comes from theta equals beta, and then this loop starts here when theta is, I don't know, say gamma, and this piece right here is theta equals delta, then we would do the integral from alpha to beta and then subtract from that the integral from gamma to delta. So the shaded area would be integral alpha to beta 1/2 r squared of theta d theta minus the integral from gamma to delta, sorry, a shitty delta, 1/2 r squared of theta d theta. But the trick is definitely recognizing what is gamma, what is delta. And the way you would find that is by looking at the sine wave in the rectangular coordinates. So this would have to have come from something looking a little bit like this. This first guy right here, where we first dip beneath the x-axis, that would have to be your gamma. And then delta here would be this. I'll try to draw you a better delta. And your alpha here would be 0. And your beta here would be coming from this guy. So in other words, you need to practice drawing these curves. You need to treat it like an entirely new skill. Your graphing skills from the rectangular coordinate system are useful because you'll need them to draw the rectangular graph, but the polar graph is going to be an entirely new skill. Fernando asks a really good question. The answer is there is a relationship between them, but it's not an algebraic relationship. It's a calculus relationship. And you'll be able to learn all about that at the end of Calc 3 when you talk about what's called the Wronskian? No, Jacobian. So if you search Jacobian matrix, you can find a little bit how to relate them. Basically, you find a transformation. The polar coordinate thing, and I know I'm starting to go over time here. The polar coordinate thing here is that horizontal lines turn into concentric circles and vertical lines turn into rays emanating from the origin. And if you can find a good GIF, let's just try a few. You can find a good GIF, then you'll be able to see. Watch what happens to this guy. Is it going to finish? Yeah, there we go. So you see what happened. Try to track a vertical line in the original. The vertical axis here. Try to track where this goes. Still that vertical axis, but now it gets wrapped up into a circle. Let's see if I can find some more. Nah. So it's nice to watch the whole plane transform, but just the plane without any curves in it, nah, that's the same. All of these are broken, okay. I know I've seen something like what I'm looking for right now. but I don't know where. It's been so long. No. But remember when we graphed our first few polar functions, we graphed r equals a constant and we graphed theta equals a constant. What we learned there is that the analogous concept to a horizontal line is a circle centered at the origin, and the analogous concept to a vertical line is a ray emanating from the origin. So if you apply that transformation to the whole plane at once, you see this crazy wrapping up. Where could I find this? Maybe under conformal map. Yeah, we're getting closer. Conformal map, polar. Nah, but it's something kind of like this. I do have to get out of here now, unfortunately. Yeah, kind of like when you fold up a dumpling. That's actually a good analogy. So I want to say just before we go, you guys have been wonderful. It's been a real pleasure. Online teaching and learning is very hard, and I'm grateful, so grateful for all the work that you guys have put in. You've done a wonderful job communicating with me, and I look forward to working with any of you in the future who ever want to take another class or talk with me. If you are panicking about your grade, come see me in office hours so we can talk about your options. I'm going to be admitting people one by one and taking my time in office hours today to make sure everybody who has a concern like that can talk to me. Do not wait to talk to me about grades, because today is the last day I can kind of get in there and strong arm things as far as registration is concerned. After today, I lose the ability to do that, and we are stuck with what we have. There's always the option to file petitions and whatnot, but you know, that's not fun. So yeah, you guys have been wonderful. Remember to do the study guide problems. Remember to grind out any homework that you haven't finished yet, and watch for exam 3 to show up in Canvas today. Prep for the final hard over the weekend. I will do my best to put together a review for the final, maybe like an extra office hour or something like that sometime over the weekend. But it's going to depend on how things are going here with all the other stuff I'm dealing with. So watch Canvas announcements, stay on top of the work. If you have any grade questions, come see me in office hours. Otherwise, you know, I hope to hear from you guys in the future. If anybody's interested in the math team moving forwards, I know I've talked to a few folks about that. Santa Fe has a wonderful group of competitive mathematics students, and I'm the faculty lead there. So if anybody wants to talk about that stuff, please feel free to reach out to me. We're going to see how we'll do it in the fall, but most likely right now we'll continue doing whatever we can do online. All right, that's all I got for you. That's Calc 2. So yeah, come see me for Calc 3 or differential equations if you want to. Otherwise, I hope you all have a wonderful future. Good luck on the final. And come see me in office hours or email with any questions. All right, take care, best of luck. And yeah, Morgan, I would love to practice speaking French. So that sounds like fun too. All right, take care, guys.